Okay, welcome everyone to today's TCS Plus talk. Today we're very lucky to have Shachar Lovett, but before we start the talk, let me just make a few announcements. So first of all, the next talk will be on an unusual day. It'll be 3 weeks from now, roughly, except on the Tuesday of that week instead, where we'll have Hao Huang talking about his breakthrough resolution of the sensitivity conjecture. And about a month after that, we're going to have Jason Lee speaking about finding k-cuts in a graph. Today we're using Zoom, which may be new to some of you. So please, if you have questions or technical difficulties, you can feel free to ping me in the chat. TCS Plus is a joint effort. I'm one of the organizers, but this is also organized with Clément Canon, Anindya Day, Thomas Vidic, Oded Regev, Ilya Rajenstein, and most recently, Salil Shram has joined our organization efforts. Okay, without further ado, let me introduce the speaker. Today, we're lucky to have Shachar Lovett speaking, and he'll be speaking on recent improvements to the sunflower lemma. And he's a professor at UCSD. His interests are in theoretical computer science and mathematics, with a particular focus in computational complexity, randomness, pseudo-randomness, algebraic constructions, coding theory, additive combinatorics, as well as high-dimensional geometry. So without further ado, Shachar, I'm going to ask you to present your slides and we can begin the talk.
Okay, thanks, Gautam. Okay, so let me share my slides. Let's see here, 1 second. Perfect. So can you see the slides?
Yep, that looks great.
Okay, perfect. So yeah, so this is all joint work with 3 students. So it's with Ryan L. Weiss, so who's a grad student at Princeton, with Kewen Wu, who's an undergrad at Peking University, and with Jiapeng Zhang, who was my student at UCSD and is now doing a postdoc at Harvard. So this is all joint work with them. And my goal is, to tell you about the work we did, sort of trying to understand better the sunflower conjecture. And in fact, I have sort of, 2, I'd say, main goals. One is I want to sort of go over some high-level themes that went to this work, and sort of try to explain a bit, how they helped us in this work. But I think they are useful, like in many areas, not just for this specific problem. And then I actually want to spend most of the time going through the technical details. So my goal is at the end, you will see all the technical details that go into this proof. And in particular, the 2 themes I want to emphasize, and this work is going to be sort of one instantiation of them, is that one is that somehow this bridging TCS and math that we all know and love, and the other one is this paradigm of structure and randomness that seems to be very, very useful for many, many problems. So let me just speak briefly about those before I start talking about this concrete work. And just can you hear me just fine?
Yeah, we can hear you great.
Perfect. Okay. So first of all, this bridging TCS and math, I know we all use math, for various problems we care about, but I want to argue that this is sort of a 2-way street of not only that we use math, but we also generate new math. And also, of course, we generate math for our own problem, but I think that sometimes this computational thinking that was developed in TCS is useful for problems in math that, on the surface seem to have nothing to do with computation. And there are several of, I wrote in the bottom of several of well-known examples. And in this work, I'll show you another example, how computational thinking was useful to study a problem that is purely in combinatorics and seems to have nothing to do with computation. But you see at the core of it, we will use sort of computational ideas to study it, to understand it better. And this other one is sort of this very well-known framework of structure versus randomness. And one way to see it is to say, when you study some class of objects, which could be, graphs or functions or whatever you want to study, then you can think of them as either having some sort of structure that is useful for your arguments, or looking random, being pseudo-random. This is one type of, structure versus randomness of dichotomy. And another one that comes up maybe in other applications is that maybe you don't have a dichotomy, but objects can be partitioned into 2 parts. One part is structure, the other one is pseudo-random. And with either one of these sort of frameworks, many, many problems so fall into one of these frameworks. In this work, we'll be in this first one, where this the dichotomy, but you should also remember there was a second one. And usually what we call structure or pseudo-random really depends on the application. But usually you define one and the other one is just a complement. So in this work, we'll say we'll have some type of structure that's going to be useful. And when you lack this structure, we're going to call it pseudo-random. And then the question will be, what can we say about pseudo-random objects? Sometimes it's the opposite, right? Sometimes pseudo-random is what's more natural to define. And again, there are many examples. So here I wrote some examples, in combinatorics, in number theory, where, all of these works are basically based on defining appropriate notions of structure and randomness and try to study them. So, okay, so without further ado, let me talk about this specific work, which is about sunflowers. Okay, so this is a sunflower, but we won't actually be studying flowers. We'll be studying sunflowers in combinatorics. And so here is a sunflower in combinatorics. So an R sunflower is a collection of R sets with a specific intersection pattern. So every element either belongs to, well, one of the sets or all of the sets, or maybe none of the sets, but let's ignore those. Like for example, if I have 3 sets, so you can see some elements. So can you see the cursor here? So some elements belong to all of the sets, some to just one of the sets, but we don't have any element that belong to 2 out of the 3 sets. And of course, there could be elements in none of the sets, but I wouldn't care about them. So I mean, surprisingly, sunflowers are very, very useful. So they come up in various applications because it's a very interesting intersection structure and sort of it's useful. And if you want to keep one image in your mind, then this 3 sunflowers is a good picture to have in your mind. So for this talk, you might as well just be thinking about 3 sunflowers. Of course, you can't talk about R being two sunflowers, but any 2 sets are a 2 sunflower. So this only becomes interesting once you have 3 or more sets. Okay, so the basic question that we'll try to understand is this Ramsey type problem, which says if I give you a set system, so a set system is just going to be a family of sets, a collection of sets. It's also called a hypergraph. I'll call it a set system, just family of sets. And the basic question is going to be, how large should this set system be so that it has to contain a sunflower, let's say with 3 or 4, or some number of petals. And that's going to be the basic question. It's a Ramsey type problem where we're saying, if I have a large enough object, then it must contain some structure, some underlying structure inside it. In our specific case, this structure is going to be sunflowers. And again, this question actually came to be in basically, there are 2 variants of this problem. So this question was, in fact, first asked, and this notion of sunflower defined in this sort of seminal work of Erdos and Rado from 1960, where they said, well, how do we bound the set system? We bound the side of the sets. And for the most part, in this talk, I'll be talking about this variant. There is also a second variant called the dős-Szemerédi sunflower, where we don't bound the side of the sets, but we bound the side of the universe. This came about 20 years later. And both of them found many, many applications, both in math and in TCS. In this talk, I will not be talking about applications. I'll just be talking about these 2 basic combinatorial questions. So let me speak a bit about each one of them. So here's the Erdos and Rado setup. So here we'll be assuming that we have a set system where all the sets have exactly the same size W. W is going to be the width of a set, the number of elements in the set. And you can also think about all sets having size at most W, it's going to be the same thing. But for simplicity, let's just think about all the sets having size exactly W. And think of R, which is going to be the size of the sunflower that we were trying to find, to be fixed. And again, a good example to keep in mind is R equal to 3. And then, so Erdos and Rado in their paper actually proved what's known as the sunflower lemma that said that, well, if a set system is large enough, then it must contain a sunflower. And the bound they proved is W factorial times R minus 1 to the W. And again, if you think as R as constant, let's say 3, then you see the dominant term here is W factorial. It's roughly W to the W. And the proof of the sunflower is in fact very, very simple. I mean, it actually fits in the bottom of this slide. I'm not going to show you the proof now. I'll show you the proof in about 10 minutes when we're going to start discussing proofs, because that's going to be a good starting point toward discussing our proof. So you will see the proof of the sunflower lemma, but only in 10 minutes. But it is you'll see it's a very simple, clean proof. It's based on this very simple inductive argument. And what they asked is this tight? So one thing they've observed is that, well, there are examples of exponential size sets that don't have R sunflowers. So for example, here's one concrete example. Think of your universe as having W times R minus 1 elements, and you break them into buckets of size R minus 1, and your sets have exactly one element in each bucket. So you can do the math and see this set system has R minus 1 to the W set, and it does not have an R sunflower. So what they proved that the sunflower lemma is tight up to this W factorial factor. So the whole question here is, do we need this W factorial factor or not? Or if you think of R as being constant, is the right order of magnitude exponential in W or W to the W? So it's a subtle question. It's about the sort of base of the exponent. It is exponential in W, but the question is the base of the exponent constant, or does it grow with W? Is it W? So what they conjectured in the original paper is that the right answer should be some constant to the W. Okay, so even if, so if R is 3, then with some constant to the W sets, you must contain a 3 sunflower. So this was this is what's known as the sunflower conjecture, and it's been open for 60 years. And as you'll see, until very recently, there wasn't much progress on it, even though people cared about this question. So I'll tell you a bit about the progress in a couple of slides. Let me first talk about this Erdos-Szemerédi variant. So the Erdos-Szemerédi sunflower question is where we don't bound the side of the sets, but instead we bound the side of the universe. So we have a set system on n elements. Sets could have whatever side they want, but you can think of size n over 2. That's a good number. And turns out this is a special case of the Erdos-Rado sunflower lemma and the sunflower conjecture. So if you take the sunflower lemma and you plug it into this framework, you get the following result. That if you want to have an R sunflower for every constant R, then the number of sets you need is exponential in n minus some constant root n. Okay, and this constant depends on R. So you can get that, and then the sunflower conjecture translates into having the bout not being exponential in n minus root n, but in n minus some constant times n. So this would be like this is the analog of the sunflower conjecture when we bound the side of the universe. So you see there's a gap here, like n minus c root n versus n minus cn. And here actually, this conjecture is known to be true when R equal to 3. So in the base case with R is 3, Nasland proved that the Erdos-Szemerédi sunflower conjecture is true. And the proof is based on this polynomial method that was used in this breakthrough work of Kurt Levenpach to understand, the capset problem. And Nasland's proof is a variant of this polynomial method. So it gives this very, very clean, sharp bound for the case R equal to 3, but it doesn't seem to generalize for larger R. And this seems to be a common phenomena for this polynomial method that when it works phenomenally well. It's like magic, but it's also very subtle. Somehow it doesn't generalize well. So people, like for many variants of these capset problems, we don't know of a way to generalize a polynomial method to get comparable bounds. And then it's also similar here, where it works for R equal to 3, but it doesn't work for R being 4 or larger. So part of the motivation for our work is trying to find sort of more, I would say, robust techniques to try and study such problems. Okay, so let me tell you a bit about our results. So from now on, I'll just be focusing about this Erdos-Rado setup. So let me remind you, it's a family of sets, a set system, where all the sets have exactly the same size, W. And to be concrete, from now on, I'll just be focusing on R equal to 3. So the question is, how large should the set system be to contain a 3 sunflower? Okay, so what's known? So what Erdos and Rado proved in 1960 is a bound of W factorial times 2 to the W. 2 is R minus 1, so it's 2 to the W, which is roughly W to the W. And this has stood for many years until Kostochka, about 20 years ago, improved the exponent by lower order terms. But this was the first asymptotic improvement, as far as I know. And then last year, Fukuyama improved the bound, improved the exponent from, let's say, almost W to something like 3/4 W. And what we're going to prove is we're going to basically improve the base to roughly log W up to, and then and again, you can think of log W to the order W if you really want to, but you can actually optimize the exponent to actually being very, very close to W up to low order terms, which seems to actually be important for some applications. For example, one application where I know this is important is Ben Rossman has an application to monotone circuit lower bounds where he actually cared about this, getting the exponent being very close to W. But anyways, log W to the constant times W. You can think about that. And so what I want to tell you now is, what ideas go into this improved bound. Okay. And any questions so far? No. Okay. So yeah, just raise your hand if you have questions, and then Gautam is going to unmute you. Okay. So let me talk about the proof. So from now, I'm just going to be talking about the proof. So again, like I told you, the two main ideas that would come across in this talk are these two paradigms. One is this structure versus randomness. That's going to come up again, again, again. And the other one is this TCS and math bridge. And more concretely, what we're going to do is say, well, set systems have this equivalent viewpoint as DNFs, disjunctive normal forms. And this would actually sort of, suggest that we might be able to use tools that we use in TCS to study DNFs in order to study set systems. So we'll get into that later. So there was one place where having this dual view was very, very useful. So let's start with the structure versus randomness. So actually, that's a good point to maybe tell you the proof of the sunflower lemma, because that's going to be a good starting point for our proof. So what I want to prove to you is if a set system is big enough, it must contain a 3 sunflower, and the concrete bound is going to be W factorial times 2 to the W. So let's do that. So the proof is induction on W. And the first step is this sort of base case saying, well, if my set system contains 3 disjoint sets, then we are done, right? Because 3 disjoint sets are a trivial sunflower. There are 3 sets where no element belongs to more than 1 set. So that's going to be like a trivial sunflower. And then we're going to ask, what if this doesn't happen? Well, if this doesn't happen, then I claim that F must contain 2 sets whose union intersects all other sets. Why? Because if I take one set, either it intersects all other sets and we're done. If no, there's a disjoint set. Let's take that one. Now we have 2 sets. Now, by assumption, there won't be a 3rd set, disjoint for both these 2. So the union of these 2 sets would intersect all other sets. Okay. So in particular, there is an element in these 2 sets that belongs to many sets in the set system. There's an element that belongs to F over 2W sets. Why F over 2W? Because there are only 2W sets. So at most 2W elements in the union of 2 sets. Remember, each set has size W. Right? So there's a common element in many sets. So now what do? We just restrict to all the sets containing this one common element. So now we have fewer sets. But now in our restricted set system, all of the sets contain this one element. So we can just remove it and continue. So we just use induction for W minus 1. And you see the bound that you get is 2W times 2W minus 1 times 2W minus 2 and so on, which gives you this W factorial 2 to the W. So this is it. This is a proof. So I hope you can all agree that this is like a simple proof, a simple inductive proof. And to me, at least, the main reason I got interested in the sunflower conjecture is because this proof seems so simple, and yet 60 years later, people weren't able to improve it significantly. So the question is, how can we sort of better utilize structure in set system to try and understand this better? So to do that, I want to make one sort of very, very useful definition that's going to come up again and again and again in this talk, which is the definition of what's called a link. So let me spend some time defining links. So I have a set system F, and T is some set, not necessarily in F, some set in the universe. And the link of F at T is another set system defined as follows. First of all, we go over all sets in the set system that contain T as a subset. We just keep those, and then we remove T from all of them. Okay, so this is a link. So just to give a couple of examples to make sure that we are all on the same page here. So if F is my set system, so it has these 5 sets, what is the link of 1? where I should go through all the sets containing 1. So I have 2 of them, this one and that one. And I should remove 1 from both. So I have the set 2 and the set 3, 5. So this is the link of the set 1. What is the link of the set 2, 3? I should find all the sets containing both 2 and 3. So I have, here's a set and here's another set. And I remove 2, 3 from both of them. So I get 4 and 6. Okay, so this is a definition of a link. So that's going to come in handy. So why are links useful? Well, it's because of the following observation. It's enough to find sunflowers in links. So if a link contains a 3 sunflower, then the set system also contains a 3 sunflower. And the reason is very simple. So if my link contains a sunflower, so in this case, it's going to be, let's say, S1 minus T, S2 minus T, and S3 minus T are a sunflower. Then if I add T to all of them, then it will still be a sunflower. So finding sunflowers in links is good enough. So now we have, now that we understand that, there's a very reasonable approach, which is to say, if a link is large, we should reduce to this link and try to find a sunflower there. So then now let me sort of go through the proof of the sunflower, go through the proof of the sunflower lemma again, but now using the language of links. So now again, it's induction on W. And the first case, then, if there is a link of a single element that is big enough, restrict to this link and use induction, right? So if there is an element X, where the link of this single element is big, in this case, big would be F over 2W, then we just restrict to this link. Now all the sets have size W minus 1, use induction. And so this is having a large link. And of course, the complementary case is if all links are small. And then basically we say F must have 3 disjoint sets. So I have the proof here. It's basically the same proof as before, right? So I mean, I'm not going to repeat it. But basically we have these 2 cases. That's a different way. It's an equivalent way of viewing the proof of the sunflower lemma. Either there's a large link of a single element, in which case we reduce to this link, or if all the links of single elements are small, we can just prove that the set system contains 3 disjoint sets and we're done. Okay, it's an equivalent viewpoint. But now that we have this equivalent viewpoint, we might hope to try and generalize it. So what's going to be the generalization? So we have again a set system. And let's assume that our goal is to prove the sunflower lemma with some bound k to the w, where k is some parameter depending on w. So, right, so if your goal is to prove the sunflower conjecture, k is going to be a constant. If your goal is to prove the sunflower lemma, the original one, k is going to be 2w, and we'll try to get as small k as we can. Okay, that's going to be the goal. So so again, in the sunflower lemma, they just use links of 1 element. But we can use larger links, why not? So now we can say, well, there is a structured case where there is a large link, right? If there exists a link, if there exists a set T, where the link of this is large enough, and large enough is going to be k to the w minus t, then we can just use induction, right? We can just reduce to this link and just use induction. So now the pseudo-random case is going to be, what can we say if this fails? So if this fails, we're in this pseudo-random case where all the links are small. And then our goal will be to prove that then we can say something about the set system. So now we just need to worry about this pseudo-random case where all the links are small. Okay, that's going to be how we use this structure versus pseudo-randomness framework here. So now let's go there. So we have pseudo-randomness, lack of structure. So let me make a definition, which is going to be very similar to what we had in induction, slightly weaker definition. I'll talk about the exact distinction towards the end of the talk. So here's another important definition. That will be our pseudo-random definition. I'll call a set K spread, set system K spread, if all the links are small, and concretely, if I go to links of a set T, it shrinks down by a factor of at least K. So if I go to links of a single element, it shrinks by a factor of K. If I go to links of 2 elements, if I look at, then I shrink by K squared and so on. So the links shrink exponentially fast with some parameter K. Okay? And then what is our goal? Our goal is to say, what is a minimal K for which we can argue that if a set system is K spread, then it looks nice. So the sunflower lemma says, well, if K is more than 2W, then F must contain 3 disjoint sets, right? This is what the sunflower lemma proved. And in fact, they only cared about sets T of size 1. So it's the weaker definition. And the question is, what can we get if we assume this for all sets T, not just for sets T of size 1? So what we're going to prove is that if you use it for all sets T, you can decrease K from linear in W to something close to log W. And that's going to be how we're going to prove our results. We're going to prove that if a set is K spread, so if a set system is K spread, with K is something like log W, then it's going to contain 3 disjoint sets. So that's going to be the main technical result here. Okay. So now the question, how do we do it? How do we prove that if a set system looks random, in that case, links shrink, then it must contain 3 disjoint sets? That's going to be our goal from now on. Now, to do that, we're going to sort of use this dual viewpoint of set systems and DNFs. So let me define DNFs. So DNFs, I mean, I'm sure you all know what DNFs are, but let me define them nevertheless. So DNF is a way to represent Boolean functions, which is an OR of end of literal. So a literal is a variable or its negation. So here's an example of a DNF. So I have terms. So each term is an end of literals. And the DNF is an OR of terms. So it's an OR of end of literals. And in fact, for the purpose of studying sunflowers, it will be enough to study monotone DNFs where there are no negations. So there are no literals, just variables. Because I will just be studying monotone DNFs. And my claim is we can identify set systems with monotone DNFs. So why? I mean, actually, I think it's easiest to see it through this example at the bottom. I mean, you can see the formal definition in the middle of the slide, but I think it's easiest to see it at the bottom. It's just a very syntactic identification, right? If I have my set system, I just identify every set with the end of the variables. So like the set 1 to 3 is identified with x1 and x2 and x3. And then, I take OR to say what are the different sets. So you see, it's a very syntactic identification, so it sort of seems stupid. Like, why is this useful? We just identify one way of representing sets of numbers with a different way. But actually, we're going to see the deeper connection here. But that's going to be the identification. So the whole point is that now we can start asking questions about set systems that are natural for DNFs, but that might not be so natural when you study them as set systems. So here's a natural question for DNF that has been studied a lot in TCS. How many satisfying assignments do they have? Right? Like, do they have one? Are all of the assignments satisfying? Is a large number of them? These are questions commonly studied in TCS. And actually, what we're going to study here is what fraction of assignments is satisfied in a DNF. And we actually need it for not just for the uniform distribution, but also for bias distribution. So here's another definition. The p-bias distribution that I'm going to denote by UP is going to be where I'm going to sample inputs to be 0, 1, where the probability for being 1 is some parameter p. Right? So the smaller p is, fewer inputs are 1, it's going to be harder to satisfy a monotone DNF. And the question that we're going to be studying is, given a DNF coming from a set system, what is the probability it is satisfied under the p-bias distribution? Okay? And I want to show you why this question is in fact relevant to finding 3 disjoint sets. So let me make one definition. It's going to be the following definition. So I have a set system, which is I'm going to denote always by this capital F, curly capital F. And then small f is going to be the corresponding monotone DNF for this set system. Now I'm going to say that f is PQ satisfying if the following thing is true. I sample inputs from the p-bias distribution, and I ask, what's the probability it is satisfied? And that's going to be more than 1 minus q. So again, you don't have to remember this definition, I'm going to repeat it later, but it's just asking, what is the probability that the DNF is satisfied under p-bias distribution? Okay, so this seems like a reasonable question to ask for DNFs, but now let's see what this question translates to when we ask it for set systems. So it's going to be the following question, and you see it's going to look less natural when you view it for set systems. So first of all, what is a p-bias distribution? Well, it's just going to be the p-bias distribution over sets. So I choose these sets in my universe where each element is included with probability P independently. And then what is the analog of a DNF being satisfied? Well, remember, every term in the DNF corresponds to a set in the set system. So when is a term satisfied? Well, if all the variables in it are 1. So if all the variables in it are in the set W, right? Think of the W as all the set of all the elements that I'm going to assign 1 to. So we're going to get the following equation. So I'm sampling a random set from the p-batch distribution, and I'm asking what's the probability that there exists a set in my set system contained in W, right? That is going to be the analog question of asking what's the probability that the DNF is satisfied. So we say that a set system is PQ satisfying if this probability is at least 1 minus Q. Okay, so what I hope you can agree to is that these two questions are the same technical mathematical questions, but somehow they seem more natural when you study DNFs, and they seem less natural when you study set system. But it will become useful to study this question. So let's see why. So I'm going to prove to you now the following lemma. And the lemma is, if a set system is 1/3 satisfying, then it contains 3 disjoint sets. Remember, our goal will be to prove that a pseudo-random looking set system contains 3 disjoint sets. So this lemma would show that we can sort of switch from this combinatorial question to this more analytical question of proving that it is satisfying with some specific constants. Okay, and here's just a definition at the top of, if you don't remember it, of satisfying. So let's do the proof. It won't be too hard. It will actually fit in the bottom of this slide here with a reasonable font. So let's do it. So here's a proof. The proof is actually by thinking of the following random process where I'm randomly coloring the elements of the universe with 3 colors, red, green, and blue. So each element is independently colored, either red or green or blue. And RGB are the marginal distributions, and you can see that each one of them has a marginal distribution of U-third, right? The red elements come from this U-third marginal distribution because each element is red with probability 1/3. And then let me ask, what is the probability that my set system contains a monochromatic red set? A set where all the elements in it are red. Well, what is this? This is exactly as asking, what's the probability that there is a set in my set system that is contained inside the red set? And this is exactly how we define satisfying, right? So I'm sampling R from a U 1/3, and by my assumption, Q is 1/3. This is more than 2/3. So with probability more than 2/3, there is a monochromatic red set in my set system. And of course, by symmetry, the same holds for green and blue. So now we can use union bound and say, well, this means that with positive probability, there are a red set, a green set, and a blue set in my set system. And remember, so if I have an all red set, an all green set, and an all blue set, they must be disjoint, right? They can't have any common elements. So these red, green, and blue sets are 3 disjoint sets. So we're using this random coloring strategy to prove that my set system contains 3 disjoint sets. Okay? So what we've just proved is that in fact what this analytic property of being satisfying allows us to deduce that my set system contains 3 disjoint sets. So now all that we have to do to conclude the proof is to prove that if a set system is pseudo-random, then it is satisfying for some constants. And you see there's nothing special about third. If I wanted to get 5 sunflowers, I could just take 1/5, 1/5. So there's nothing magical about this 1/3. This is just what you need to get this to work for, to get 3 disjoint sets. So now, all that we have to do to conclude the proof is to prove that a pseudo-random set system, or equivalently a pseudo-random DNF, is satisfying with high probability. Okay, that's going to be our goal from now on. So actually, that's going to be our main technical result, that spread set systems are satisfying. So just recall the definition. So again, we have a set system with sets of size W. We say it is K spread if the links shrink down by a factor of K. So you can think of it as every element belongs to at most 1 over k fraction of the sets. Every pair of elements at most 1 over k squared, and so on. So links shrink exponentially fast. And satisfying basically asks what the probability that the p-biased set contains a set in the set system should be large. And here's going to be our main technical lemma. If k is something like log w, then a pseudo-random set is satisfying. Okay, so this is going to be what we're going to prove from now on. It's going to be the last piece needed to complete the proof. So just a recap of the proof structure so far. So we're trying to put this the set system of size k to the w, where k is going to be something like log w. Then it must contain a 3 sunflower. There was a structured case and a pseudo-random case. A structured case where f contains a large link. Concretely, there's a set T where the link ft shrinks by a factor of k to the t, at most k to the t, so it's still link large. Then we use induction on this link. We prove by induction this link contains a 3 sunflower, and hence my set system contains a 3 sunflower. Otherwise, we are in the pseudo-random case, all the links are small. This is what we call k-spread, where the links shrink down. We had this technical lemma that we need to prove that in this case, the set system is 1/3, 1/3 satisfying. And we saw this corollary that this implies that the set system contains 3 disjoint sets, so we're done. Okay, so the one last piece is proving this lemma, which is what I'm going to do from now on. But before I do it, are there any questions? Yes, Puya.
Yeah, so this lemma that you're proving, is this tight if someone wants to improve the bound on sunflower?
Yes, so, the answer is yes. And I'll talk about tightness towards the end of the talk, but for most of these arguments, the log W is tight up to low order terms. Up to like log W terms, it is tight. But I will talk about tightness towards the end of the talk. Thank you. Any other questions? I guess not. Okay, so let's continue. So here's the last piece of the puzzle. We have to prove that spread set system, again, to remind you, pseudo-random set system are satisfying. And equivalently, pseudo-random DNFs are satisfied with high probability. And again, we all know that random restrictions sort of simplify DNFs, so fixing variables to constant simplify DNFs. What we're going to prove, in fact, if you study pseudo-random DNFs, then actually mild, very mild random restrictions also simplify them. And that's going to be the main way we're going to prove that. So we're going to prove that basically the switching lemma can be improved if you are dealing with pseudo-random DNFs and not with arbitrary DNFs. So random restrictions. So first of all, what is a restriction? So again, we have a DNF now. So Boolean function represented as a DNF. A restriction is just fix some variables to constants. And the rest you leave unfixed, that we call a lie. So a restriction is specified by a string 0, 1 start with the n, where star are the live variables, and the rest are 0, 1. And if f is a DNF, then I denote by f row with row the restriction, is just plugging in this restriction and then crucially simplifying the DNF. Okay, what is simplifying? Let's look at this example. So here I have a DNF, and here's my restriction. So I fixed x1 to 1, x3 to 1, and x4 to 0, and here's plugging this in. So here I haven't simplified anything yet. So I can simplify this DNF in 2 ways. First of all, some terms are going to become false, so I can remove them. And then other terms are in fact going to be implied by other terms, like x2 and x6 I can remove because it is implied by x2. So by simplifying a DNF, I mean remove redundant terms, and a term can be redundant in one of 2 ways. Either they become false, or they are implied by previous terms or other terms. Okay, so this is what I mean by simplifying a DNF under a restriction. Now, what is a random restriction is just a restriction where I choose it at random. So I choose it to be star with some probability, and then otherwise uniformly 0, 1. And I'm denoting by p the fraction of fixed elements. So 1 minus p is the fraction of alive variables. So the switching lemma, the first proved by Hastad, and also reproved by Beam and by Razborov, is to say that if f is a with W DNF, which means every term has W variables, which corresponds to our case where all the sets have W elements, right? Then if you fix almost all of the elements, so if you fix 1 minus something like 1 over W fraction of the elements, then DNF simplifies. So if you only leave a small fraction alive, something like 1 over W fraction of the variables alive, then a DNF simplifies a lot, and concretely it becomes a low depth decision tree, but that won't really be important for us. So what we know is for adversarial DNFs, you need to fix almost all of the elements. But what we're going to prove is for pseudo-random DNFs, it's enough to fix much, much fewer. So what we're going to prove is that if the DNF is pseudo-random, then it's enough to fix actually to leave most of the variables alive. So you only fix a small constant fraction of the elements, and that's already going to simplify the DNF. Okay, that's going to be the main technical contribution here. Analyzing pseudo-random restrictions, analyzing random restrictions for pseudo-random DNFs. So here's going to be the lemma that we're going to prove. So F is a k-spread set system, reminding you it means that links shrink down exponentially with base k. Sets have size W, so this corresponds to a monotone DNF. Actually, it turns out for monotone DNFs, it's enough to study random restriction where you just fix to 1 and star. You don't need 0. For general DNFs, you need 0, 1, and star, but it doesn't really make a big difference either way, so you can think of either variant is fine. It doesn't really matter. So what we're going to prove it for, if I choose the random restriction with p is something like 1 over k, or more concretely, poly 1 over k, then the DNF simplifies. What do I mean by simplifying it? It basically reduces to with W over 2. So by fixing a small fraction of the variable, something like 1 over k, I reduce the width by a factor of 2. So of course, once you know that, then the obvious thing you want to do is to repeat this, right, until it shrinks the width to nothing. So if you repeat this log W times, basically you get a constant 1 DNF. So that means if we fix something like log W times 1 over k fraction of the variables, then the DNF becomes true. Right, so of course what we want to do is we want to choose P to be something like 1 over log W, so that P times log W is a constant, like a third, which is what we're trying to analyze, right? That's going to be like this U 1/3 probability. So we want P to be maybe a third times log W, which means that K has to be something like log W, which is one reason why this technique gets stuck at log W, because we have to repeat this log W times. Every random restriction simplifies the DNF only by reducing the width by a constant factor. Okay, so this is maybe one reason why we get this log W. So now I want to prove this lemma. Okay. And any questions on this lemma, what we're trying to prove? Oh, good. Okay. So now I want to prove to you that, one second, just check the time. Okay. So I want to prove to you that mild random restrictions simplify pseudo-random DNFs. So again, we have this k-spread system, and F will be the corresponding monotone DNF. And now what do we do? Again, for monotone DNF, it's enough to study restrictions where I just fix a few variables to 1. So equivalently, I just sample W, which is a set of ones, from some p-biased distribution, and p should be very small. And I want to say, if I fix the variables in W to 1, how does this simplify my DNF? That's going to be the question. So here's how it does it. Let's see. So when does a term in my DNF, which is equivalently a set in my set system, simplify from with W to with W over 2? Well, when does this happen? Well, it happens if there is another set S prime, maybe the same, maybe S prime is S, but S prime with the following two properties. First of all, S prime is contained in S union W, and this just means that if I fix the values in W to 1, then S prime, and then S implies S prime, right? If S is satisfied and I fix W to 1, then S union W is satisfied, so S prime is also satisfied. Right? So S prime is implied by S union W. And additionally, if I remove the variables W from S prime, the width shrinks to W over 2. So if I fix these variables, and I look in the restricted DNF and I remove them, then S prime now shrinks to with W over 2. So this will be the condition when a term satisfied, when a term simplifies. Okay, so now what we're going to prove that after that most terms in this DNF simplify. So let's do that. So again, here's a setup. And now actually concretely, if you want to reduce from W to W over 2, you need P to be something like one of the root K. It doesn't really matter. So we say a term or a set in F is bad if it doesn't simplify. Meaning there is no S prime with these properties. So we're going to prove that basically they're not bad. Most sets are good. Only few sets are bad. How do we do that? We use an encoding argument. And to show that bad sets can be encoded efficiently, and hence most sets are good. And that's going to be inspired by similar encoding argument like by Razborov and Beam were used to prove to have alternative proofs for switching lemma. Okay, so let's do that. Now finally, we're going to do the calculation. So I want to encode bad sets efficiently, and here you're finally going to see why this K-spread condition is useful, because so far we haven't used it. So we need to use it somewhere. So here is going to be the place where we're going to use this pseudo-random assumption. So I want to encode the bad set. In fact, I'm going to encode the bad pair. So it's going to be a bad, so W is a random restriction. You remember, fixing these values to 1, and S is going to be the bad set or the bad term in the DNF. So first I'm going to use W prime to be the union. And then I'm going to say, let S prime be the first set in my set system contained here. And so assuming before I start this, I order the sets in my set system in some arbitrary order. And I just take the first one. Of course, there is one because S is here, right? But there might be a previous one. Maybe, I don't know. So I just choose it. And then I look on the intersection between S and S prime. And I claim that because S is bad, because S only intersects W by a small amount, this intersection must be big. So this is an exercise. You can check it later if you want. So they have a large intersection. And now finally, we're going to use the fact that T is a big set. And I know S belongs to the link of T, right? Because T is a subset of S. So instead of telling you what S is, I can tell you what S is inside this link. And that's a small set system. So I need fewer bits to encode the index of S in this set system. So now let's actually do the calculation. Well, how many sets do I have? Well, S is in sets in F, so I have that many sets. And that means slightly cheated. Instead of choosing W to be P biased, assuming I'm choosing it uniformly from all the sets of density exactly P. It's going to be roughly the same thing, just the calculations are slightly easier. So I have N choose P n sets of density exactly P. Right, so that's a total number of pairs. How many bad pairs do I have? Well, let's do the encoding. Well, first I want to encode W prime. W prime, if I had these Pn elements originally in W, and then I need to add maybe at most W more, because S is another set, and it has at most W more elements. So now I need to encode something like that, and choose Pn plus W, which is roughly this N choose Pn, and what you lose here, if you do the calculation, is roughly 1 over P to the W, because I need to encode W more elements. Now, in the second step, we don't need to pay anything, because once we figure W prime, this is just a deterministic process. Now, the third step is simple. I mean, I have the set S prime, T is a subset of it. I need to pay at most 2 to the W to encode T. And now, finally, the last step is where we gain. Because to encode the S's, I just need to tell you what is the index of S in this link. And this link is much smaller than F. It shrinks by a factor of K to the W over 2. And again, this W over 2 is big because the set T is big. So now if I put this all together, so this is the last technical slide I have, you just put them all together. So here is a total number of sets. Here's a number of bed pairs. Now the encoding site, or N choose Pn cancels. The size of F cancels. What do I have here? Again, so the important terms are 1 over P to the W, and then I lose K to the W over 2 here. So you can do the method if the P, the fraction of elements I fix, is much more than something like K to the minus half, then most sets, this is much, much smaller, so most sets are good because I encoded bed pairs by much fewer bits than what I need to encode a general set, okay? So I know these last few slides will be technical, but the whole point of them is to show you this calculation, which is here is the place where we gain from having a pseudo-random DNF, okay, because these links shrink. So after this slide, I'm going to have some summary and some, so telling you about how tight this is and some open questions. So maybe now is a good time for questions about this last part of the proof, this encoding argument. Okay, no questions. Let me continue. So summary. So here's what we proved. So again, we have a set system with a set of size W. Sunflower is constant R. Sunflower lemma. This was proved by Erdos and Rado. Give this type of bound. R minus 1 to the W times W factorial. If this happens, if F has that many sets, it contains a sunflower and R sunflower. Now, the sunflower conjecture is that these are the constant to the W. What we proved is we improved this W factorial to something like log W to the W up to low order terms. In fact, there's a new paper by Anupra where he reproves this using sort of, information theory, and his proof is more succinct than ours. I mean, that might also be a good source to read. But again, these low order terms, if you really care about them, there are some log W factors. If you want to see the details, are in the paper. So this is what we prove. And the question is, okay, can we hope to get the sunflower conjecture using our techniques, or do you need new techniques? Maybe before that, so just to remind you, the high-level approach is using this structure versus randomness paradigm and this sort of viewpoint of set systems as DNFs. And we have this high-level proof overview. But maybe since we only have 5 minutes left, let me just go quickly through how tight this is and what can we hope to do to get better bounds. So how far can we push this framework? So one question to ask is this. So our technical lemma we use in coding was to say that if a set is k-spread, then it is satisfying with some values like 1/3, 1/3. How small can we choose k to guarantee that? So we showed k could be at most something like log W, but actually you have examples where k needs to be something like log W up to low order terms for that to be true. So if your goal is to prove that k-spread set systems are satisfying, or equivalently k-spread DNFs are satisfied, then you need log W. So we have examples. And in fact, even if you just want to bypass this satisfying argument and say, well, what if I just want my set system to contain 3 disjoint sets? So forget about this satisfying condition. Maybe that's like the wrong way to go about it. What if I just want to prove that my set system is sort of pseudo-random, it's k-spread, it must contain 3 disjoint sets. Then even then, you need something like log W up to low order terms. So generally, in this approach, we will not get to something better than log W. But actually, there is one ray of hope, because you can slightly refine the notion of pseudo-randomness, for which you might hope to prove something like that. So let's do that. Yeah, I don't know what other line here. So remember, this is our definition of, this is the pseudo-randomness definition we used here. A set system is k-spread if the links shrink by a factor of k, if you add more elements. But and again, we have examples where this will not ever get us beyond the log W barrier for the base. But actually, if you think about what we need, actually it's okay to get something stronger as our pseudo-randomness assumption. Let me call this k-bound and just to give it a different name. So it's actually enough to assume the following pseudo-randomness assumption. So my set system has at least k to the W sets. And a link size is at most k to the W minus t. So this looks, if the set system is exactly k to the W, then they're the same, right? But if the set system is more than k to the W, which could be, then they're not the same. This is actually stronger, although they're very, very similar. So you could ask, what if I use this slightly stronger definition for pseudo-randomness? Is this going to help us? Well, it turns out that if you care about satisfying, then even for this one, you need log W. But if you really want to talk about 3 disjoint sets and not think about satisfying, then for this one, we don't have counterexamples. So maybe one concrete question to ask, and maybe make this conjecture, which is maybe this is the right condition. Maybe if you have this notion of pseudo-randomness, then you must have 3 disjoint sets. And maybe a good starting point is to prove you have 2 disjoint sets. And even this we don't know how to do. So that's maybe one option of how to do better by studying this more refined notion of pseudo-randomness. And here's my last slide. So just to say that, well, random restrictions, we use them a lot in TCS. And the new thing here is that we apply them not to arbitrary objects, not to arbitrary DNFs, but to pseudo-random DNFs. And for pseudo-random DNFs, you can actually apply them with much, much better parameters. So my question is, can we hope to use similar techniques to study other problems in TCS, or also maybe to study other Ramsey problems in combinatorics? And there are many Ramsey problems in combinatorics where there are big gaps between upper and lower bounds. So in this talk was about the sunflower conjecture, but there are many other problems. So the generalizations of capset, there are looking for 4-term AP3 sets, Hayes-Jewett. There are other questions in geometry where we don't have the right bounds. So let me stop here and thank you.
Cool. Thank you very much, Shachar. We have time for questions now. Are there any questions? Puya, go ahead. Sorry, Puya, I think you might have been muted again. Feel free to unmute yourself and ask a question. And then we have another question from Gopal afterwards.
So I was just wondering, so when you're using K-spreadness to imply 3 disjoint sets, and you said you have a counterexample for smaller values of K, could we hope to, so does the counterexample also not have 3 sunflowers, or is it just 3 disjoint sets?
No, that's a good question. No, it does have sunflowers.
Okay.
But it does not have 3 disjoint sets. So it's said that if you're hoping to say that if your pseudo-random contain a trivial sunflower, so if you interpret trivial sunflower as 3 disjoint sets, then this would be a barrier. But there might be a different type of a trivial sunflower that we haven't thought about.
Okay, thanks.
I think next we had a question from Gopal.
Hi. You hear me?
Yeah, go
Yes,
ahead.
yes.
Yeah, this is a very basic question. At the beginning, you showed 2 versions of the sunflower conjecture, the Erdos-Rado version and the Erdos-Szemerédi version. And you said that they are kind of rough analog. Are they actually exactly formally the same, or it's just analogs?
Okay, let me just go there quickly. Sorry. I try to skip back to the book. And either just start from scratch. Go to the relevant slide.
Okay, so the Erdos-Rado sunflower conjecture is a stronger conjecture than the Erdos-Szemerédi conjecture. Is that correct?
This is correct.
Okay, thank you.
All right, are there any other questions? I noticed, yeah, if anyone else has unmuted themselves, you can feel free to just ask. Okay, I guess I have a question. Are there any immediate applications or implications of this improvement to the sunflower lemma to other fields? For example, I guess maybe this is immediate or not immediate, but you mentioned Ben Rossman had some improvement based on this?
Yeah, so I think with the one with Ben Rossman, I spoke with him a few days ago. It still seems to be require maybe some more things. I know that, to be honest, I'm not sure. We tried to do some literature survey of all the places where these have been used, about too many of them. Various places I know, like in what is it called? Like the various types of the exact bound, like the FPT type algorithms. I think just these new bounds get like improved bounds for some other products, but I don't have like a one concrete killer application. But this is true, just somehow, yeah. I mean, it's been around, this lemma has been around for like 60 years. I mean, there are like hundreds of things that use it, so I don't know.
Yeah. I would argue it's a killer app in itself. That's cool, but it is as it is.
Yeah, thanks.
All right, are there any other questions? All right, if not, I will in a second take us offline, so anyone can ask questions, you know, that they want after that. But let me just remind people that roughly 3 weeks from now, we'll have Hao Huang talking about his resolution of the sensitivity conjecture. 2 weeks after that, we will have another talk, which is yet to be scheduled. And then 2 weeks after that, Jason Lee will be talking about K-cuts and graphs. All right, I'm taking us offline. Thanks.